for inviting me. Yeah, I'd like to talk about some joint work with Phil and with André Carvalho. This is really a long-term project that's been going on for several years. I want to talk about some aspects of it. So, you know, some of this stuff is just like in Jono's talk, some of it's already published. Some of it is still being written up. So let me start by introducing the main ingredients in what I'm going to talk about. I
have to click on the screen.
Oh, right, I'm not.
Okay, just click on the screen.
Right. Yeah, so I wish that I'd coordinated the Yene a bit, because we're going to have a lot of slides which look very similar, starting with tent maps. So a tent map is just a map of the interval. You choose a slope S between 1 and 2, but just like Yene, pretty soon I'll be restricting between root 2 and 2. And it's just the unimodal map that has a branch of slope S and a branch of slope minus S. One of the reasons that tent maps are interesting is that they provide models for more general unimodal maps. So if you take any unimodal map, that is any map with a graph that goes up and then down on the interval, as long as it's got positive topological entropy, well, then its dynamics is modeled by a tent map, a specific tent map, the one which has the same topological entropy as the unimodal map that you started with. Modeled in the sense that there's a semi-conjugacy down here. So we've got an increasing surjection from the interval to the interval, which semi-conjugates the dynamics of your arbitrary unimodal map to the dynamics of the tent map with the same topological entropy. And I say that semi-conjugacy is explicit. It's explicit in two senses. It's explicit in that you can actually write down a formula for it, which means that you can plot a graph of the semi-conjugacy like this. It's also explicit in the dynamical sense that you can describe exactly which intervals are being collapsed to points by this semi-conjugacy. They're basins of stable periodic orbits and wandering intervals and renormalization intervals. Okay, so that's the first ingredient. The second ingredient, let's see if this button works now, yeah, is also going to look at from the point of view of a type of model. So in this setting, we've gone up one dimension. We're looking at homeomorphisms of, so a surface of finite type. It means a compact surface, but possibly with a bunch of punctures. And there's a big theorem due to Thurston from the 1970s, which says you take any homeomorphism of such a surface, then it's isotopic. If that's not a word you normally use, it just means you can deform it continuously into a homeomorphism G, which is one of three special types. One possibility is that it's finite order, dynamically very simple. Some iterate is the identity. A second possibility is that it preserves a multi-curve. So without going into the details, that means there's an invariant set of curves on the surface. You can cut along those curves, your surface falls into simpler pieces, and you can then analyze the action of G or some iterate of it on each of those pieces. And then the generic or typical case is the pseudo-Anosov case. That's the interesting one. I guess Phil will say more about this possibly after the coffee break, possibly next week. I'm not sure when he's going to get onto it. So a pseudo-Anosov homeomorphism, the key ingredients are a transverse pair of measured foliations. Okay, and that sounds like a fancy thing, but all it means is that if you look anywhere in the surface, there's a red unstable foliation and a blue stable foliation. And if you pick your coordinates right, they look just like that. And your pseudo-Anosov stretches uniformly along one and contracts uniformly along the stable one. Of course, that sounds very much like an Anosov. What makes it pseudo is that there are finitely many points where you can have singularities of these foliations where they look like saddles with some number of separatrices. And if you're not on the torus or the Oceanus or something, these are required by Euler for other characteristic reasons. Okay, so these play a huge role in the theory of the dynamics of surface homeomorphisms. And, you know, I want to emphasize again, they play that role because they're models. So just like we had last time on the last slide, any unimodal map, semi-conjugate to one of these very special tent maps, any surface homeomorphism is semi-conjugate to the pseudo-Anosov, which is isotropic to. In principle, the dynamics of the pseudo-Anosov are easily understood, and that means that all the easily understood dynamics down here is present in the arbitrary surface homeomorphism that you started. Okay, so I want to talk, as the title of this talk suggested, about a generalization of the results to something called measurable pseudo-Anosovs. So again, we're in the case where we're looking at homeomorphisms of surfaces of finite type. These pseudo-Anosovs are measurable, so there better be a measure on our surface, which is non-atomic and positive on open surface. Okay, so a pseudo-Anosov preserves this transverse pair, a stable and an unstable foliation, and everywhere, except at the singularities, those give you a nice, I'll go backwards, a nice product structure on the surface. They're very regularly arranged. A measurable pseudo-Anosov, by contrast, preserves what we call a transverse pair of measured turbulations. So again, we've got red and blue, we call them streamlines now, rather than leaves of the turbulations. One of them is uniformly expanded, and one of them is uniformly contracted. What's the difference is that there's no nice local product structure, which means that you know exactly what these things look like in the neighborhood of any point. There's a much weaker condition that the full measured subset of the surface is covered by what are called tartans, which are things like this. So the point is that these are collections of stable and unstable streamlines that sit in a nice topological configuration with each other. I've deliberately drawn these not straight and diverging from each other and so on. But the point is, whenever you see one of these tartans like this, there's also a whole bunch of other stuff which is doing completely different things coming in the gaps. Okay, so in this picture here, you know, we've got this tartan, but there's no local product structure because there's all this stuff coming in like this. There's another little tartan that you could draw down there, but inside that, on a smaller scale, there'll be more things coming in. Every scale that you look at, something is destroying any hope of a local product structure. Okay, so in a little bit, I'll say something which will indicate just how complicated these things can be. I mean, a picture doesn't do justice to the complexity that these turbulations can have. Okay, so it's basically the same idea, but we relax the requirement for a local product structure. Okay, so why would you do that? So whenever you come up with a new definition, I guess there are two things that you want to be sure of. One thing you'd like to be sure of is that your definition is strong enough that if I just tell you I've got a measurable pseudo-Anosov, you can prove something about its dynamics. And this definition is strong enough. So just from the definition, you can show that these things are transitive, have dense periodic points, sensitive dependence on initial conditions. With some additional conditions, you can show that they're ergodic. So there's enough structure there to get your hands on the dynamics. Okay, so you'd like to know a new definition is strong enough you can do something with it. You also want to know it's weak enough that there are examples. Okay, and there are examples of these things. In particular, you can find a whole continuously varying family of sphere homeomorphisms, which are all measurable pseudo-Anosov. And these arise naturally, actually, from the family of tent maps, which is why I started talking about those. Okay, so these are two quite different topics, and with half an hour left, I can't talk about both of them. So what I want to do actually is to focus on this second thing here, and show you how measurable pseudo-Anosovs arise in nature. We didn't make the definition and then look for them, right? We constructed this family and then thought, what is it that the maps in this family look like?
Excuse me.
Hello.
Hello. Could you please say again what was the definition of tartans?
I'm sorry, I didn't hear that.
Could you please say again what was the definition of tartans in the previous slide?
Definition of tartans.
Okay, so I haven't, I won't be saying again because I haven't given you a definition of a tartan, but a tartan is essentially, you have these two turbulations which are made up of immersed lines covering a full measure subset of your surface. And a tartan is basically a collection of parts of stable and unstable streamlines which intersect topologically as I've drawn here. So obviously, typically an infinite collection of such art. In fact, tartans are very interesting if the intersections of the stable and unstable streamlines have positive measure. So I don't know who to look at. Maybe I can look at the camera. I don't know if you can see me if I look at the camera.
Yes, that's okay then.
Is that all right? Yeah.
Yes.
For question, does they need to cover a full measure subset in this neighborhood shown in the picture?
No, and typically they won't.
I see.
In all interesting examples, they won't. You're right. So if you're trying to cover the full measure of this thing, well, you'd have this tartan, and then you'd have another tartan in there, and then you'd have another tiny tartans in there. You'd have to use counting many tartans to cover the measure in this region. Okay, so here is another slide that looks very much like one of René's. The kind of ingredient which connects tent maps and sphere homeomorphisms is inverse limits. So René talks about this, but we have a dynamical system. Typically, this is interesting when it's surjective. And the way to think about the inverse limit is, well, the inverse limit consists of points of x, but you attach to each point a ribbon which has its past history in it. So you say, well, my point is x0, but by the way, that point came from x1, and by the way, x1 came from x2. You specify the history of each point. And then the dynamics of f is obviously modeled on here. If I have a point x0 together with its history and I hit it with f, well, it goes to f of x0 together with its history. And because you know the history of each point, this thing is obviously invertible. I want to go backwards. I just say, well, I came from x0 with that history there. Okay, so it's homeomorphism. The projection onto the first coordinate, that is, this point we're thinking of as being x0 with a history. So the map that sends x0 with its history just to x0 obviously semi-conjugates these things. And again, as René said, if you have any invertible dynamical system, which has this as a factor, well, it factors through the inverse limit. So it's the minimal invertible system which has the one you're interested in as a factor. You pay for the convenience of constructing a homeomorphism, as we'll see, and as René explained very eloquently, in a complicated topology for the inverse limit space. Okay, so we're interested in inverse limits of tent maps. Again, this is a point that Yoni made, so we're going to restrict to slopes which are bigger than √2. That prevents our tent map from being renormalizable. Inverse limits are most interesting if you have surjective systems. The tent map, as originally defined in black here, is not surjective. There's a big gap at the top. And so when looking at inverse limits, you tend to restrict it to its core or dynamical interval. You can see there's a little red subinterval here, which is invariant and under which the tent map is surjective. Okay, so we've got a family of core tent maps from the red intervals to the red intervals. Slopes are anything between √2 and 2. And we're going to look at the inverse limits of those tent maps and the natural extensions, the homeomorphisms that they induce on the inverse limit. Okay, so what do these things look like? Let me start with the simplest case, which is a full tent map, the one of slope 2. So what's the point of the inverse limit? Well, you take a point x0 somewhere in the interval, and you specify a history for it. And because this is the full tent map, if you take your point x0 here, well, it has two preimages, a lower one and an upper one. So if I've got my point x0 in the interval here, I can choose its first preimage either to be in the lower half of the interval or in the upper half of the interval. And then that preimage itself has two preimages. So if I'm in the lower part of the interval for the preimage, I can be in the lower or the upper part of the interval for its preimage. Similarly, if the preimage of x0 is in the upper part of the interval, well, it can be in the lower or the upper part of the interval, the preimage x2 of x1. And so on. So we make a sequence of binary choices. And so above x0, we get a Cantor set of possible histories. X0, of course, can be anything in the interval. And so we get an interval across a Cantor set. We get a Cantor set of intervals in our inverse limit. Okay, but that's not quite the whole story, because it's not quite true that every point has two preimages. There's one point, x equals 1, which only has one preimage. And so actually taking the lower preimage for x equals 1 here is the same as taking the upper preimage. And so this point here is the same as that point there. And these semicircles are not part of the preimage, they're identification lines. They're showing actually if you're at x equals 1, your first choice was an illusion. It doesn't matter whether we chose this point or this point, they're actually the same point. And so they give the same point in the inverse limit. Yep, and similarly, if x1 happens to be 1, well, then there's only one preimage, and that will give identifications here. These identifications come in the case where x2 is equal to 1, and so on. Yep, so we get a Cantor set of intervals with identifications on their endpoints. And actually, this is exactly the canaster bucket handle continuum. It's probably the simplest example of an indecomposable continuum. Okay, but already pretty complicated. And this is the simplest thing that we found for an inverse limit of a tent map. Yep, any questions about it? Okay, so that is the simple case. What happens if you don't take the full tent map, but you take some slope which is less than 2, so your core tent map looks like that? Well, in that case, there's a whole bunch of points, the points lower down here, which only have one preimage. And that means that, you know, this diagram on the top half, it's all there, but on the bottom half, you've cut a bunch of it off. And similarly, when you look at the second iterate, there'll be a bunch of stuff which no longer has two preimages because it falls into this interval. And so basically, you're cutting out bits of your inverse limit of the full tent map because there's a whole bunch of things that only have one preimage rather than two. But if you look at this picture, it looks like actually the situation is not too bad. I mean, there's some combinatorial work you'll need to do to work out which bits are cut off, but really it looks like the stuff that's left, we've still got ample sets of horizontal lines. Okay, but what the picture looks like and what's actually happening, the picture is extremely deceptive in this case. So let me tell you some facts about these inverse limits of tent maps. I'm going to start with the positive facts, which say, well, these are relatively simple. So it's still true that the fibers, the intersections with each vertical line, those are still Cantor sets. So that's nice. This is going to be very important for what we do later, that if you take a typical point in the inverse limit and look at its path component, then that is a bidense immersed line. Okay, so almost every point, if you look at its path component, it winds around here, just in the way that it looks from the picture, as if it ought to wind around. Okay, so those are good things. They say it's simple. Here are some bad things, and the worst things happen when the turning point of your tent map is dense in the interval. So first of all, the picture deceives you. This thing is nowhere locally the product of a Cantor set and an interval. Okay, we've still got Cantor set in the vertical fibers, but it's nowhere a product of Cantor sets and horizontal intervals. This is, I think, an astonishing result. This thing is not just self-similar, it's self-similar on steroids, right? Because in every neighborhood, you don't just have a copy of this picture, you have a copy of this picture for every parameter in the family. Now, every single one of these different inverse limits appears in every neighborhood of any single one of them, well, any single one of them where the critical orbit is there. So there's a lot of structure going on there that we just can't see. Another thing, you might think that, components of points are at least typically going to be, well, at least going to be arcs. They are typically arcs. They're all going to be arcs. I don't even know how this happens, but you can get solitary points. Maybe Yeno has some intuition about this. There are solitary points in this, points which are alone in their path component. There are spiral endpoints which kind of spiral down to an endpoint here. There's all sorts of stuff going on in this picture, or not in the picture, going on in the inverse limit, that you couldn't imagine from the picture. And let me just mention what Yeno also talked about, the Ingram conjecture, that for different values of the slope, these inverse limits are non-homeomorphic. So I think, in fact, unless something's happened recently, this has been proved for the non-chord tent maps, the ones not in the dynamical, that's barred through in the steam match, right, a few years ago. Actually, that's still unknown for this particular model of the chord tent maps. Right. Okay, so I guess the moral is that these things are complicated, topologically complicated spaces. So this is the main theorem, I guess, that I'm talking about. So let me start with this diagram on the left and start with what we already know. So this bit at the bottom here is the semi-conjugacy between the natural extension of the tent map, the homeomorphism on the inverse limit, and the tent map itself down below. And I said, you pay for the fact that you've created a homeomorphism up here by having horrendous topology in the inverse limits. And I guess the main statement of this theorem is, for just a very small price, actually you can turn this horrendous topology back into nice topology. Okay, so there's another semi-conjugacy from here going to a family of sphere homeomorphisms. So the topology has become nice. We've still got homeomorphisms. And this semi-conjugacy is very mild. So all of the fibers of the semi-conjugacy, except at most one, have cardinality at most three. Okay, so this isn't collapsing enormous sets. It's taking pairs or triples of points and collapsing them to single points. Okay, it says all the fibers except at most one have cardinality less than or equal to 3. There's one fiber which is different. That can be still finite, but of arbitrary cardinality. It could be countable, or in the worst case, it could be a Cantor's. And I should say that we've stated this here for tent maps down below. It works equally well for, you know, the logistic family or your other favorite family of unimodal maps, provided you've got some typical dynamical niceness properties like negative Schwarzian derivative, that sort of thing. Okay, so there are two questions which naturally arise from this theorem. One question is, you know, there are all these nice fibers where I'm just collapsing pairs or triples of points, and there's one that's bad. So, you know, what determines that exceptional fiber? And the other thing is, I've constructed a family of sphere homeomorphisms. What sort of sphere homeomorphisms are they? And you know, if you're paying attention and you've got some idea where this is going, the answer to this one is they're going to be measurable pseudo-Anosovs. That's where, so they've got a lot of structure to them as well. Okay, so I'm going to kind of talk a little bit vaguely about the ideas and the proof of this, and then a little bit less vaguely. But any questions about the statement? Okay, so here's the picture of the inverse limit that I saw before, and I want to use it just to kind of try to give the vaguest idea of the ideas in the proof. So the first one is, you know, we're meant to have a semi-conjugacy between the natural extension acting on this inverse limit space and a sphere homeomorphism. So what does that semi-conjugacy look like? What does it collapse together? And a kind of good first idea is that what it does is we've got a bunch of vertical Cantor sets and it just collapses all of their gaps. Yep, so the Cantor set in each fiber will become an interval, and somehow that collection of intervals together is going to make a sphere. Okay, this is misleading, remember, because this picture is misleading and there's a lot more going on than just interval. Well, actually, in this picture, there is only interval cross Cantor set, but in general, there's something more complicated. So you can see that if you collapse the gaps in these vertical Cantor sets, well, you're going to get a whole bunch of, you're going to get a whole bunch of points that aren't identified to anything, all the buried points in the Cantor set. You're going to get a bunch of points that are identified in pairs, the gap endpoints. And then because of these identifications here, when I identify this point to this one, well, that point is the same as that one, and that's identified to this one down here. And that's going to give me a triple of points which are identified, corresponding to each of these little nubs at the end here. So that's roughly speaking where this thing comes from. So the second thing to say is I haven't quite embedded this thing in the plane because these things are not really art, they're just indicating where identifications are. But at least you can believe this thing can be embedded in the plane. I'll say a little bit more about that later. That's kind of the first step in the proof, is to embed these things nicely in the plane. So let me say something about this particular example, which is, if you look at it, there's a threeness to this example. So if you know about prime ends, you probably don't have any difficulty believing that this thing has three non-trivial prime ends. But if you don't know about prime ends, you can still see that there's a threeness to it, right? And there are three tunnels into this inverse limit. So I can come into it like this and go around here and come through there and keep on winding around like that. Or there's another tunnel where I come in here and go down there, and a third tunnel down here, right? When there are just those three tunnels, they correspond to three non-trivial prime ends and a kind of threeness in the picture. But actually, it's not just a threeness, it's a one-thirdness, because this isn't just a topological space, but we've got a dynamical system here. And what the dynamical system does is it stretches in this direction, contracts in that direction. This part here is going to be sent across that part there. This part here will go around there and so on. And in particular, this tunnel gets sent into this tunnel gets sent into this one, and this one actually gets sent. This goes here, gets sent into this tunnel. Yep, so the tunnels are being rotated with a rotation number 1/3. Yep, so there's a 1/3ness about this picture. And just to show you another example, to show that they're not always 1/3ness, This picture, well, there are 7 tunnels into the attractor. I've got 1, 2, 3, 4, 5, 6, and one you can barely see, a 7th one up at the top there. And those are mapped around, as in the order I indicated them. First one goes to the 3rd one, goes to the 5th one, and so on. There's a 2/7 rotation going on here. Okay, so there are rational numbers or numbers, rotations on the circle of prime ends associated with each of these examples. So what are those? Okay, well, what those rational numbers are what are called the height of the Hent maps corresponding to the examples that we're looking at. Yep, so height is a stratification of the space of unimodal map. So it works more generally, but just in the context of Hent maps, so I've got parameters between √2, 2, and the height associates to each of these Hent map parameters a number between 0 and 0.5. And it does it in such a way that there are whole intervals of parameters which get sent to each rational height, whereas if you have an irrational height, there's a unique parameter which the Hent map has that height. And the height basically tells you what is going on. The questions I asked, what's the exceptional fiber? What do these homeomorphisms look like? Well, the exceptional fiber, the one that doesn't have cardinality less than or equal to 3, if you're in the interior of the set of parameters which have height m/n, then that fiber has cardinality n. Okay, so in particular, because the interiors of these intervals make an open dense subset of the parameter space, there's an open dense set of parameters for which all of the fibers are finite. As you move to the endpoint of one of these rational height parameter intervals, the endpoint, the fiber is countably infinite. And as you might guess, the other case is where the height is irrational. So these are these isolated parameters. They're a particular irrational height. And then the exceptional fiber is going to be a Cantor set, which is rotated around with that rotation. And what about what the dynamics of these sphere homeomorphisms is like? Well, there are 3 cases, and they're all, measurable pseudo-Anosov is the most general of these. So the headline is all of these sphere homeomorphisms are measurable pseudo-Anosov maps. So in fact, in each interval of rational height, so height 1/3 or 2/7, like the pictures that I showed you before, there's a unique value of the parameter for which this sphere homeomorphism is actually a genuine pseudo-Anosov homeomorphism. More generally, whenever your Hent map is post-critically finite, or in fact in the irrational height case, you get what's called a generalized pseudo-Anosov. So generalized pseudo-Anosovs are much nicer than measurable pseudo-Anosovs. Like pseudo-Anosovs, they have nice foliations everywhere. The only difference is that instead of having only finitely many singularities on the foliation, they can have countably many. But these countably many singularities only accumulate on a finite set. So there's only a finite collection of really bad points for a generalized pseudo-Anosov. That's the post-critically finite case. And in other cases, these things are all measurable pseudo-Anosovs. So that's the motivation for us to study measurable pseudo-Anosovs, is that they're what appear in this family.
So they will be pseudo-Anosov. Critical point is periodic.
Yeah, the critical point, not always when the critical point is periodic. For very special periodic critical points, yeah, just one of each height. Yeah, so right, so mostly when the critical point is periodic, they're going to be generalized pseudo-Anosov. The pictures that I drew before actually are periodic critical point, because that's the only ones I can really draw.
Two slides back, so that it wasn't periodic the previous slide. It was height one. Oh, no, height 1 yes. So this one is which slope?
I think at a guess the leading sequence is 1 0 0 1 0 1 0. Probably. It looks like a period 7. Yeah. What the slope is for that?
Yeah. Yeah.
Okay, so let me finish just by.
Excuse me.
Hello.
Hello. Sorry, about the regularity of the semi-conjugacy, is it continuous or it's just measurable?
So is what continuous? The
family is a continuous in T.
the family is continuous, yes.
No, the semi-conjugacy. Is the semi-conjugacy from S2 to the inverse limit continuous?
Yes. Yeah.
Okay.
Yes, everything is continuous.
It was again what is station on pre-images of rational points. So we have 1 point pseudo-Anosov, and do you have a then set of generalized pseudo-Anosovs or?
Right, because you have it. So within, so suppose that the height is equal to a third. So you have an interval of parameters, a closed interval of parameters with height a third. Here in the middle, you've got this kind of magic point where you actually get a pseudo-Anosov. And then whenever the critical orbit is finite, which is going to be a dense set of parameters in here, you get a generalized pseudo-Anosov, and then when the critical orbit is not finite, which I guess is a full measure set of parameters in here, you only get a measurable pseudo-Anosov. Any other questions? Okay, so the main ideas of the proof. So as I said, I drew these pictures of inverse limits, and I said, well, you can imagine just from the pictures that you can embed them into the plane. The pictures almost are embeddings of those things into the plane. Well, we start off with a very explicit embedding of the inverse limit into a sphere, actually, and then a sphere homeomorphism, which extends the natural extension. Okay, so the inverse limit is something topologically complicated. It's got dynamics on it, which is the natural extension, and we embed that dynamical system into a sphere homeomorphism. And that's actually done. So Yene mentioned Barge and Martin as well, but this is a different paper by Barge and Martin, which gives a very general way of embedding inverse limits and natural extensions into surface homeomorphisms. Okay, so then sitting inside the sphere, we've got this embedded copy of the complicated space, the inverse limit. And as we can imagine, this is, if you know about Moore's theorem, this is going to be a Moore's theorem type argument that we get an invariant, non-separating, monotone, upper semi-continuous decomposition of the sphere, and every element, except for the exceptional one, intersect the inverse limit in between 1 and 3 points. Okay, so when we quotient by that decomposition, the quotients on the inverse limit, they are going to identify between 1 and 3 points. Okay, and then we apply Moore's theorem. So if you know Moore's theorem, then there's nothing for me to say about this. And if you don't know Moore's theorem, it's a bit of magic that enables you to collapse out bits of the sphere and end up still with a sphere. Okay, so the work in this part really is in being very careful. Right? I mean, this embedding has to be explicit. Everything is described in coordinates. You carefully construct this decomposition and prove that it has the required properties. Okay? It's being very, very careful. That's the hard part of this part of the thing. So what that gives you is a bunch of homeomorphisms of topological spheres. Yeah, I've taken these spheres sigma s that I've embedded into, those are abstract spheres, right? They're different for every parameter s. I've constructed different decompositions for each one, and I've factored out by those decompositions. I've got these homeomorphisms ks, which are all on different spaces here. The decompositions are ks invariant, and so they induce homeomorphisms ls between these topological spheres. But you know, these are abstract topological spheres, and a priori there's no connection between them at all. Okay, so how do you turn these family of homeomorphisms on different spheres into a continuously varying family of homeomorphisms of a sphere? This puzzled us for a year or more, I think. And then, you know, so by accident, we found exactly the ingredient we need, which is a three-dimensional Moore-like theorem due to Dyer and Hamstrung, which precisely enables us to turn these distinct sphere homeomorphisms into a continuously varying family. And then let me just say that you know, these sphere homeomorphisms are meant to be measurable pseudo-Anosovs, and that means they're meant to have invariant turbulations. And if you remember back to when I first talked about inverse limits of tent maps, I was saying, well, they've got some nice properties, and one of the nice properties is that almost every point lies on a bidense, that the path component of it is a bidense immersed line. The nice thing about measurable pseudo-Anosovs is that your turbulations only need to cover a full measure subset of the surface. And so actually we just throw away everything which isn't on bidense immersed lines, and those nice path components give us the unstable turbulation. Because of the results of that I told you about self-similarity, about having copies of every inverse limit in the family embedded in arbitrary small open sets in each one, these turbulations behave in a very complicated way. Yeah, and so going back to the original picture that I drew about turbulations, you know, that's why they never give you a nice local product structure. There's always details at every level, you know, finer and finer detail at every level. And actually the stable turbulations cut off at the bottom here, they just come from the pi0 fibers. Okay, that's roughly how that argument works. Okay, I've overrun by a minute or two, for which I apologize, but thank you very much for your attention.
It's possible to provide an example how at least one simple to this map FF look like?
How what looks like the
one of this map from FS is possible to describe somehow.
Right, so the pseudo-Anosov ones I can describe quite easily, but you know, if you know pseudo-Anosovs, I can you know, I can give you a train track or a Markov partition. Yeah, I mean, sorry, I'm not. They look right. I guess. I guess they look like this, right? I mean, the space is a sphere, so you have to imagine that you've taken each of these vertical lines, you know, I mean, it's a bit of a simplification, but it's roughly right. You take each vertical line and you factor the gaps. Okay, that gives you a whole bunch of intervals, and then actually where the exceptional fiber comes from is from sewing everything up around the outside to make a sphere. You know, the outside means, you know, all of the accessible. So we sew everything up to make a sphere. But basically, the sphere just looks like this with the gaps collapsed. And the dynamics just looks like what I said it looks like. We stretch by the slope of the tent map, we contract. This bit here gets sent over this bit here. You know, it's tent map-like dynamics on that space. So I guess that's a picture of it. You can collapse the gaps and fill in the details.
Any other questions? No more questions, so let's thank Toby again.